This is a video of worksheet week 9. So in this first step, there's supposed to be KOH here, right? And then essentially what's going to happen is in this first step, you're going to deprotonate this phenol, make the phenoxide. And if you remember from, this is all one, you remember from your benzene chemistry exam, you end up making this, only the ortho product, and that's because this potassium's right here and it coordinates to both oxygens. And then in step 2, you're going to protonate them. Right? And then when you come here, this step 1 is going to be to deprotonate them, and then step 2 is going to be just to alkylate them. So your final product should be like this. So this is another way to make esters. You can deprotonate the carboxylic acid. You can make esters this way as well. All right, this second one here, this is going to use Jones. You're going to get to a carboxylic acid. We use the SOCl2. So this is step 1. You're going to get to the acid chloride, and then step 3, you put an alcohol in with the acid chloride, you will get the ester. So this is like a standard way to make esters. For this, if you get to choose the reactions, you almost always want to go to the acid chloride and then make whatever derivative you want. All right, for 3, where this first reagent here makes the methyl ester. You can look in your notes for the mechanism for that. And then an ester, remember with LAH, when we learned this during the carbonyl section of the class, is going to make a primary, losing a carbon, primary alcohol. Good. All right, and then these next ones are decarboxylation. Remember, for this decarboxylation, we make this pseudo 6-membered ring. And then if I show mechanistically what happens, and you can have your arrows go the other way, and I don't really care, right? You get to this, so I just follow the arrows, and I don't move any of the atoms. You get to this. And then this is going to tautomerize. So this is a gas. This is going to tautomerize to make this. Or the net result is basically you chop this. Because you have tautomerization, you can also do it if you're in the enol form. So this would just be this for the final product. And now when I look at this, you want to make sure the carbonyl has to be beta. So this is like alpha, beta. So if I do it here, for these two carboxylic acids, it's going to be like alpha, beta. They're beta to each other. It doesn't matter which one you chop off. You chop off one of them. Then if I look at the only other carboxylic acid, well, actually, alpha, beta, this one, of course, can tautomerize, become a ketone, gamma, too far away. So the only other carboxylic acid I have is this one. So it's going to be like alpha, beta, gamma this way, or alpha, beta this way. So this one can also decarboxylate. So if I draw the final product, and whether you leave this as an enol or a ketone, I don't really care. And if you chopped off this carboxylic acid or this one, that doesn't matter. They're symmetrical. There's no chiral center there, so it doesn't matter which one you cut off. So that's going to be your product there. All right, if we do mechanisms, we need to do this SOCl2 mechanism. So first thing I would do is have this come in and attack, push that up. Let's have our structures feeble out. Flush charge too. Then have this come back down, kick off the chloride. Then we can come to the next step, this chloride, and come back, attack the carbonyl. Right, now we have a neutral compound, neutral intermediate. This is our tetrahedral intermediate. And this is where you can have this come and kick this off. And you also are going to make this, continue to make SO2 and Cl minus. This is a gas, so it leaves the system. Oops, sorry, you can't see all that. It leaves the system. SO2 leaves the system. And then of course we have this positive charge here, and we will have our pyridine. Lone pair, just come in and take this to make our final product. This gas formation is what drives this reaction. So you need to have that gas formation. All right, next one. If I'm going here, what's the mechanism for this decarboxylation? Well, first I'm going to just redraw this molecule. Now we're going to go and move our arrows. And now essentially, or not essentially, exactly, I just have to do tautomerization. So when I come here, the next step, I just need some sort of base or acid. So I have a carboxylic acid, so I have to be in some sort of acid, right? Do some sort of H+. If you want to be like, Edward, how do I know which acid to use? You could literally use another carboxylic acid from this if you really, really want to, right? And then we come here to this one here, and we do that by just using some sort of base. Let's take this, like that. And again, you can use water if you want. You could use whatever. So, good. What's the last one? Oh, one more mechanism, which is here at the end. And this is how we're going to do this one. So first we got to react this with H2O. You can protonate the carbonyl first for this, but acid chlorides are extremely reactive. So whether you protonate first, whether you protonate the carbonyl first and then have water attack, or you do a second, I don't really care. I think there's a good argument for both ways. Since we're an acid, we probably should protonate this. Right, and then we can come over and take, I should probably protonate before we deprotonate, right? this carbon here. Right, and then from here, this is like the end of step 1. Then we can go on to the next step, and I can't remember, I'm running out of room, aren't I? Right, where I guess let me redraw this. Actually, I'll redraw this down here. So this is like an arrow when you do that little loop that you're just like redrawing it, and I'm going to just redraw this like this to do the decarboxylation. Now that we're here, we can come and do these arrows. Non-equilibrium. Yeah. Right, and then I can make this make a final one. The final structure. All right, that's the end of this video. Here's the whole mechanism so you can see it.